So in our previous video, we were looking at StatCrunch to simulate a sampling distribution. The goal there was to try to understand what a sampling distribution is, first just from the idea of doing it before we formalize it here in this video. So again, remember the idea there was that I was going to take a sample. From that one sample, I was going to get a sample proportion. Then the goal was to do that multiple times and look at those sample proportions from one sample to the next, since we would not expect to get the exact same sample proportion each time. So now in this video, we're going to formalize what we saw in that applet and begin to apply it to some problems. So let's first talk through this definition of a sampling distribution. So a sampling distribution allows us to model how a statistic behaves from sample to sample. So in our example that we did in the applet, our statistic that we calculated each time was p hat. That was our sample proportion each time that we did it. Now, what does that really actually mean, and why should you care? Let's go through this a little bit more specifically as well. So we generally take a sample to get a statistic and so for our example, again, our statistic was p hat. So I took a sample to estimate what percentage of all the beads were black. So that was my goal there. So this then was to estimate the population parameter So in our example, that would be P. So we took a sample, found the sample proportion that were black, where our goal was to actually figure out what percent of all the beads were black. So a sampling distribution of a statistic, and again for my statistic here I'm talking about p hat, allows us to know what types of values to expect that is what is likely to happen versus unlikely to happen. So remember, this goes also back to the idea where we talked about randomness, and randomness allows us what to expect, right? And our goal there is if we know what to expect, we can figure out how likely or how unlikely something is to happen. So that's the goal with the sampling distribution. Now let's actually write this more formally from also what we saw in our applet we did last time. So under certain conditions, which we will get to talk about here shortly, we are able to say that p hat, which remember is our sample proportion, will be approximately distributed normally. And so this will go back to what we learned in the normals video. We need to know two different things for a normal distribution. We need to know the mean and we need to know the standard deviation. Our mean here is going to be P, which is our population proportion, and our standard deviation will look a little bit different. It is the square root of p times 1 minus p over n. As a little side note here, especially if you're looking in the book, or you might see this in future videos, some people will label something that's called Q. Q, if you see it, is just the same thing as 1 minus p. So what you see here, some people may write as the square root of p times q over n. Okay? Also, we're going to do a little bit of notation here on the side. So as I said here, right, this first number that we need is our mean. So another way that we can write this p, so this p that I have written here is the same thing as the mean of p hat. And this that we have is our standard deviation. And so this square root part, we could call the standard deviation of p hat. So that's notation that you might see in the book as well as on iMath. So we'll put that here as well. So I am also going to write this as p hat is approximately distributed normal, where the first thing I'm going to write is the mean of p hat, and the second thing I write is our standard deviation of p hat. Now let's apply that to an example to see if it makes a little bit more sense. So if we go back to our example where I sampled 50 beads, and remember 40% of all the beads actually were black. So that means for our example here, our n is going to be 50, and our p is going to be 0.4, or 0.40. So then we'll be able to say that p hat will be approximately distributed normal with a mean of 0.40, and I'm going to have to do my math here for my standard deviation. So my standard deviation is going to be the square root of 0.4 times 1 minus 0.4 over 50, which gives me 0.0693. And so that up here will be my standard deviation. So then to match that to our notation above, my mu of p hat would just be that 0.40. My standard deviation of p hat is going to be that 0.0693. Now, as I mentioned up here, this only works under certain conditions. So what are these conditions that we're going to need? Well, the first condition that I'm going to need is a relatively random and unbiased sample. So this goes back to earlier in Module 2 when we've talked about unbiased ways of taking a sample. So we want to do our best to keep from any biases happening. A lot of times I will refer to this as just an RRUS, standing for the relatively random and unbiased sample. So we've got to make sure we are taking our sample in an unbiased way. Otherwise, these things will not work. My second condition is that n times p needs to be at least 10. And notice from our example, we will have both n and p. So we'll be able to check that, and we will do that shortly here for our example. And then our third condition is that n times 1 minus p, or again, some people might call n times q, also needs to be at least 10. So do these conditions hold for our example? So when we're using the applet, when I was taking the sample just using the applet, I'm pretty sure that wasn't doing anything in a biased way. So that one would work. There would be no known bias here, at least. Now let's check our n times our p for the example we just did on the previous page. So our n was 50, and our p was 0.4, and that will give me 20, which is at least 10. And then for my n times my 1 minus p will give me 30, which is also at least 10. So our conditions would work here. All right, so now that we know we have a normal distribution, we know its mean, we know its standard deviation, we can apply everything that we learned in the first module about normal distributions to this scenario. So one of the first things we'll talk about is our normal curve rule, or 68, 95, 99.7 rule, or sometimes even called the empirical rule. So we're going to see how this would apply to when we had a p of 0.4 and an n of 50. So I already have our normal curve drawn here. Remember the whatever goes here in the middle at the bottom is whatever our mean is. So if we're using our example here where p is 0.4 and n is 50, we already had done the calculations, so my mean is going to be the 0.4. Next, to use this normal curve rule, I'm going to go out one standard deviation in both directions, and that will give me 68% of my data. All right, so what standard deviation am I going to use? I'm going to be using this standard deviation that we calculated of 0.0693. And so subtracting that off would give me 0.3307, and adding it on gives me 0.4693. So then I could say, when taking a sample of 50 beads, then 68% of the time we should get between our 0.3307 as a percentage would be 33.07%, and our 0.4693 as a percentage would be 46.93% black beads. So about 68% of the time, I should get roughly between 33% and 47% black beads. Now let's go out that second standard deviation. Still, our standard deviation is 0.0693. All right, and if I go out two standard deviations, we get 95%. Doing my math along the bottom, this time I get 0.2614 by taking 0.3307 minus our 0.0693 to get that. Then on the top part, we get 0.5386 by taking our 0.4693 plus our 0.0693. So then I could also say, when taking a sample of 50 beads, that 95% of the time we should get between, and this time it's 26.14%, and 53.86% black beets. Right, then finally we could go out our third standard deviation. And this time doing our math, we would get 0.1921 and 0.6079. And when we go out that third standard deviation, we get about 99.7%. So then we could also say, when taking a sample of 50 beads, 99.7% of the time, we should get between 19.21% and 60.79% black beets. So now I know if I am taking a sample of 50 beads where 40% of all of them are black, most of the time, I mean almost all the time, this 99.7% of the time, I should get somewhere between 19% and about 61% black beets. So now I would know if I took a sample of 50 beets and I found that 75% of them were black, would that be unusual? Well, where is 75% on my picture? It's nowhere to be found. It's way out here. I would rarely ever see that happen. That's very unlikely to happen. That would be very, very unusual. Versus if I got 50% black beads, that's roughly in here. That's going to happen within our 95% of the time. That is pretty likely to happen. So it's not a very unusual value. So that's how a sampling distribution allows us to know what to expect. So let's change things up a bit by just now sampling 100 beads instead of sampling 50 beads. So first, let's talk about how would this affect our sampling distribution. First, let's talk through those conditions that we had. So do we have still our relatively random and unbiased sample? Still assuming that I'm using my applet here. I'm not going to have any known bias. So we're good there. Our n is now different. So when I take my n times my p, this time it's 100 times our 0.4, which is 40, which is still at least 10. And finally, our n times our 1 minus p will give us 60, which still again is at least 10. So my conditions will still be met. So this time we're going to be able to say that p hat will be approximately normally distributed. So let's look at our two values here. Our first one is our mean. Remember, our mean of p hat is just whatever p is. So that did not change with this example. So our p is still 0.4. Our standard deviation of p hat is the square root of p times 1 minus p over n. Since n has changed, this number will change. All right, so our standard deviation this time will be the square root of 0.4 times 1 minus 0.4 over 100, which will give us a standard deviation of 0.0490. So what you'll notice here is our standard deviation is smaller than it was when we sampled 50 beads. Neither of these things that we just found should be surprising. Remember what we saw in our applet. As our sample size got bigger, so this time we're going from an N of 50 to an N of 100. The mean didn't really change. So notice our mean was 0.4 when N was 50 and is still 0.4 when N is 100. So that sample size is not affecting the mean. However, we saw that as our sample size got bigger, our standard deviation got smaller. So we're seeing that here in our numbers as well. Our first standard deviation was our 0.0693 when we sampled 50 beads. But now that we're sampling 100 beads, it's smaller at 0.049. So that's where we're seeing part of what we saw in our simulation showing up with the formula as well. Let's talk about how will this impact our 6895-99.7 rule. What I'd like you to do here is to pause the video to at least draw the picture. You might have a bit harder time writing the sentences at first, but let's at least make sure we're getting the same numbers. Right, this is our mean. This is our standard deviation that we're going to use on the picture. So again, pause it here and try to draw the picture. All right, so hopefully our picture looks the same. So I started with my mean of 0.4. My standard deviation is 0.049. So that was the size of each of my increments here. When I went out one standard deviation, I got 0.351 and 0.449, which will give me 68% of my data. When I go out the second standard deviation, I get 0.302 and 0.498, which will give me 95%. And finally, that third standard deviation will give me 0.253 and 0.547. So first, hopefully the numbers are correct. Now we're just going to write out some similar sentences to what we had with our first example. But this time, we're taking samples of 100 beads. So when taking samples of 100 beads, 68% of the time, we should get between, and my numbers here are 35.1% and 44.9% black beads. If instead we want to find 95% of the time, we should get between, this time, our 30.2% and 49.8% black beads. And then finally, if we go out that third standard deviation, or 99.7% of the time, we should get, this time, between 25.3% and our 54.7% black beads. So notice that these numbers are a little bit different than what we had when our sample was only 50 beads. Right, so the numbers along the bottom are different. We have a larger spread when our sample size is smaller. and a smaller spread when our sample size is larger. So now what we might consider to be an unusual value is going to be different because our sample size is different. So that's how we can use that empirical, normal, or the 68, 95, 99.7 rule. Let's talk about actually using that then to find a probability. So what would be the probability that if I took our sample of 100 beads, that the percentage of black would be greater than 30.2%? So since my sample is 100, I'm going to be using the same mean and standard deviation, or basically my numbers down here along the bottom are going to stay to be exactly the same. So that'll be the first thing I'm going to do, is just put my numbers along the bottom. So I'm not changing those at all compared to the previous page because my mean and standard deviation are exactly the same. So there's those. 30.2% in decimal form is our 0.302 here. And then it says I want greater than that. So greater will tell me to shade to the right. All right, so here's what we know. This is 2 standard deviations below the mean, right? 1, 2. So I'm also going to go 2 standard deviations above the mean, which takes me to our 49.8%. And if I do that, this piece is 95% between those two numbers. But then I'm missing this little piece, so I need to figure out how much is in that piece as well. Well, remember, the entire picture adds up to 100%, and I already have 95% on my picture, so I can only right now add 5% more to my picture. But I have 2 different spots to put it in, so I'm going to split it up equally. So over here is 2.5%, and over here will be 2.5%. Same number on both sides since my normal distribution is symmetric. So I'm going to take that 95% plus that 2.5% to give me 97.5%. So if 40% of the beads are black, when we take a sample of 100 beads, we should find that 97.5% of the time that greater than 30.2% of them are black. We're going to end this video with one more example trying to use the 68, 95, 99.7% rule to find another probability. If we can. So let's look through this number. And I can already tell you if I'm going to be able to use this rule before I even dive in. Where is 33% on my picture? It's not one of these exact increments that I have on here anymore, is it? So let me go ahead and put our numbers here along the bottom, just as we have above. And this time if I find my 33% on the picture, right, it falls somewhere about right here. And we're still asked for greater, so I could shade this to the right. So see, I can't just use my 68, 95, 99.7 rule because my number here on the bottom didn't fall perfectly on one of the marks I already had here. So it's somewhere between 1 and 2 standard deviations below the mean. Well, we've talked about something that measures how many standard deviations away an observation is from the mean. So that's going to lead to our other video using the Z calculation that we'd seen before to help us find probabilities when we're no longer looking at a number that's perfectly along the bottom here.